All right. Hello, everyone. Um, Welcome to the SZ4Grads Spring webinar series. This webinar is organized by um, SZ4D and SZ4Grads. So I want to first introduce SZ4D and SZ4Grads. So SZ4D stands for Subduction Zone in 4 dimensions and is a community-driven initiative for long-term interdisciplinary research program to understand the limits and possibilities of predicting geohazards in subduction zones. So SZ4Grads stands for Subduction Zones for Grads students and graduates, and is a collaborative, interdisciplinary, and intercultural network for early career researchers studying subduction zone processes. So before I introduce today's speaker, there's some things I need to mention. So first, during and after the talk, so we hope you can fill in a survey to provide us some feedback about this webinar. So the link of the survey is already in the chat. I hope everyone can see it now. And I also want to remind that the live translated caption are also available. So if you need, you can use this function. And also we are recording this webinar, so the recording will be posted on the SZ4D YouTube channel. Another latest news we want to advertise today is the application for the Cascadia field trip are now open. So if you are interested in attending this trip, please apply using the link to the QR code, which is also pasted in the chat. Okay, all right, let's move to today's talk. So it's my honor to introduce today's speaker, Dr. Rebecca Fildes. So Dr. Fildes is currently a postdoc scholar at the University of California, Davis. She earned her PhD degree from UC Davis in 2023. So Dr. Fildes is a computational geophysicist, generally interested in earthquakes. She is particularly interested in the mechanisms that cause deep earthquakes in subducting slabs, which she's gonna talk about today. And she has also studied statistics features of shallow crust seismicity during a volcanic eruption in Hawaii. So, all right, let's welcome Dr. Fildes for today's talk about deep earthquakes.
Great, thanks for the introduction. I think everyone can hear me and see me. So yes. Yeah, today, as you mentioned, I'm going to be focusing on deep earthquakes, and in particular, kind of linking timescales between subducting slab evolution and deep earthquake occurrence. So some quick acknowledgements first. This work was done, some of this work was done in collaboration with Magali Billen, my PhD advisor, and Menno Freiters and Haoyuan Lee were current and former lab group members here at Davis, who were very instrumental in implementing a lot of things in the 2 main codes that I'm going to be talking about using for this deep earthquake problem. So Aspect and Geodynamic World Builder, which are supported by CIG. So also wanted to acknowledge them. This work was also supported by the Department of Earth and Planetary Sciences and NSF. So the overview for today's talk is, first I'll give a little bit of background about deep earthquakes, what we do know, what we don't know, where in the slab I'm talking about when I'm saying deep earthquakes. The main part of the talk is going to be part 2, and talking about how subduction modeling can be a tool to investigate these deep earthquakes. I'll talk a little bit about some previous work that's been done, and then I'll talk a lot about my updated subduction modeling methods to get at the questions I have. And then in the very last part, hopefully, if there's time, I will talk a little bit about how we can use these methods I'm presenting to investigate particular failure mechanisms for deep earthquakes. So thermal shear instability in this case. So I'll jump right into the first part and talk a little bit about the background of deep earthquakes. So this is just a very simplified cross-section showing general plate motions at the surface. The yellow cartoon stars are indicating general earthquake locations we're familiar with. A lot of us are very familiar with the shallower ones in the lithosphere or near the megathrust of the subduction zone. But the earthquakes also occur in subducting slabs all the way down to about 660, 700 kilometers deep. And so when I'm talking about deep earthquakes today, this is the part of the Earth that I am thinking about, is between this 70 to 660 kilometer depth range within subducting slabs. And just to back out a second for why do we care about deep earthquakes? Like I said, we're mostly familiar with the shallow lithospheric earthquakes in terms of thinking about hazard. But these deep earthquakes, especially the large ones, do produce geodetic signatures at the surface. So I have here just an example from a recent Nature paper where they measured surface deformation after a deep earthquake over 500 kilometers deep, and then was using that to investigate the viscosity structure of subducting slabs and the mantle around them. So this is a way where better understanding earthquakes maybe isn't as important for the hazard question, but for understanding kind of earth dynamics. And then I will say they also do produce shaking at the surface. So when I was at a earthquake and tsunami workshop in Japan, I felt an earthquake that woke me up with shaking at about 2 o'clock in the morning. That was all the way down at 375 kilometers below the surface. They've also recently been talked about a lot more in the Huanfuca slab in Cascadia, the shallower realm of deep earthquakes. Have been known to cause damage and are being considered in terms of thinking about hazard assessment. So not the first ones that we think about when we think about earthquake hazard, but they are an important part of the overall earthquake hazard thinking, and also as these, in the earlier part of the motivation, these tools of insights into kind of inner dynamics in the mantle. So if you're familiar with deep earthquakes, you might have seen them broken down into these two categories of intermediate and deep focus earthquakes. For the purposes of today's talk, I'm just going to be referring to anything below 70 kilometers as deep. So what you're seeing here is a histogram that's plotting the depth distribution of earthquakes as a function of depth for the whole global catalog. And so you can see that it's not uniform. We have a lot more earthquakes occurring in this shallower portion, and then in this deeper portion with less activity in this middle range of the slab. Excuse me. And so there's variability within the global catalog. And I'll also point out that we observe these deep earthquakes in subduction zones all around the world. But the depth profiles shown here for Kermadec and Tonga, Japan, and South America, just as two examples, exhibit very different behavior in terms of the depths within the slab that these earthquakes are occurring. So for example, in South America, we have this big sort of gap in earthquake occurrence. Kermadec and Tonga, which hosts most of the world's deep earthquakes, pretty well mimics the global catalog. And so we see a lot of variability between subduction zones and within depth of a single subduction zone. So when we think about these depths in the slab, the pressures and temperatures that we estimate to be in these regions are too high for deep earthquakes to fail by the same process that we understand shallow earthquakes to occur by. And so how these earthquakes actually occur is an ongoing investigation that is being investigated through a variety of mechanisms. So the three kind of currently main proposed failure mechanisms for how they're occurring are listed here. I'm not going to go into detail about all of them, but I'll briefly just walk through that. Dehydration and brittlement is thought to have to do with dehydration reactions and the kind of intermediate part of the slab, and people have observed double seismic zones as sort of evidence for this. Transformational faulting of the metastable olivine wedge, shown in this cartoon over here, with more in the transition zone of the slab. And then the last one is thermal shear instabilities, which hasn't necessarily had a more like depth restriction set on it, but has been investigated at more of the intermediate depths before. And I'll return to thermal shear instabilities later in the talk and talk about them in a little more detail. But overall, the question of which of these mechanisms or combinations of mechanisms are viable in the deep slab is an open one, and whether they're active in all slabs or at different depths in the slab. And so since I am thinking a lot about subducting slab deformation, I have sort of three main questions that get at this idea of linking the deep earthquakes with the longer term slab deformation that I think can help guide the investigation of whether these mechanisms that have been proposed are viable at these deeper depths in the slab. So the first one is, what are the conditions that we expect in the subducting slab at these depths? And so when I'm saying conditions, I'm talking about temperatures, stresses, strain rates, pressures. The second question is, how does the spatial distribution of these conditions compare to the observed deep earthquakes that we see? So what conditions are we seeing in the areas where we're seeing the deep earthquakes occur? And the last is, are these conditions that we're seeing in the slab where the earthquakes are occurring even viable at the deeper depths for the hypothesized deep earthquake failure mechanisms to occur? So I'm mainly going to be focusing on these first two questions about what are the conditions in the slab and how does this relate to the spatial distribution of deep earthquakes, and then I'll touch on the third question a little bit at the end. So in terms of what's sort of been proposed before or studied before, regardless of which of the three failure mechanisms I mentioned previously are viable, the general constraints for deep earthquakes to occur were proposed as low temperature and high stress. So it needs to be much colder and accumulate that high stress for the earthquake to occur. The individual failure mechanisms that I mentioned each also depend on strain rate. And a recent paper, Bill in 2020, used subduction modeling methods to propose that high strain rate was another one of these general constraints on where deep earthquakes can occur, in addition to the low temperature and high stress. And so I'm going to talk a little bit about that and move now into the subduction modeling portion of the talk and talk about that Bill in 2020 paper and then the methods that I've been developing. So I'm going to be referring to kind of the main proposal hypothesis from that study as the strain rate constraint hypothesis. And what this study did is it looked at 2D numerical models. What you're seeing here on the right is a snapshot of one of those subducting slabs from a numerical simulation, colored by strain rate, where the yellow is higher strain rate and the blues are lower strain rate. And then what's plotted here is the strain rate as a function of depth inside different temperature contours. And what she did was these subduction models were not set up to model a specific subduction zone. They were just sort of generic subduction models. But she compared snapshots of the models that were similarly shaped or characterized to real subduction zones around the world. Oops. And looked at what the observed earthquakes were in that subduction zone. So here she compared the numerical model with a 2D profile through the Chilean part of the subduction zone. And the observed earthquakes here are colored by depth. And then this histogram in the middle is just a depth profile that's counting number of earthquakes as a function of depth. And what she saw when I'm doing this for multiple profiles was that higher earthquake activity, depths where there was more earthquakes occurring, aligned with where there were higher strain rates in the numerical model. And where there were lower strain rates in the numerical model, there were gaps in earthquake activity. And so this led to the overall proposal that high strain rate is an additional constraint on deep earthquake failure. There were some limitations, though, of this study. So the models used in this particular study they were viscoplastic models, but they did not include elasticity, and they did not include low temperature plasticity in the rheology implemented in the model. And both of these are important for how the slab is going to deform and the values of strain rate and stress that you're going to get out of your model. Additionally, I mentioned that the models were not set up for specific locations. They were compared with similarly shaped slabs. But not incorporating elasticity and not having a specific location set up are important things to keep in mind when you're comparing with earthquake observations. And so by addressing some of these limitations, we can improve the types of comparisons or the level of detail of comparisons you can make between your numerical models and observations. So what I'm going to present next is some updated subduction modeling methods that I worked on during kind of the final portion of my PhD that were going to address some of those limitations and then test that strain rate constraint hypothesis with these updated models. And so I incorporate both elasticity and low temperature plasticity into the rheology of the numerical models. And I developed a method to build the location-specific subduction models to better compare with earthquake observations. And so I'm going to walk you through a little bit of the methods for that next. Oops. There we go. So this is what my numerical model looks like in terms of the model domain at just general sort of characteristics. This modeling was done using the open source code Aspect, hosted by CIG. And what I'm modeling is just a 2D domain, so a slice through the mantle that goes from Earth's surface all the way down to the core mantle boundary. It is a finite element model. So the mesh that I am solving a series of equations on looks like this, where I have very fine mesh about a kilometer scale within the lithosphere, and then I have a coarser mesh down in the mantle. A little more on the technical details is it's an incompressible model. It solves conservation of mass, momentum, and energy, the advection equations. It uses the extended Boussinesq approximation. Important things to note are my boundary conditions. So nothing can enter or leave the domain. This is a closed box. So I have free slip boundary conditions from my velocity conditions, which also is important to note that I'm not prescribing any velocities for the plates at the surface. So I have the subducting plate and this overriding plate, and I'm not telling the plates how fast to move. This is set up as a dynamic model. So the main thing that's driving this model are the density differences and the buoyancy forces within the model. I also incorporated the elasticity and plasticity that I mentioned on the last slide into the rheology. I don't have a very visual figure for this since this was done in the equations part of the model. And I also incorporate 7 equilibrium phase transitions for olivine and pyroxene. So to zoom in on the slab, my lithosphere is has a crustal component, a Hartsbergite component, and a general pyrolytic mantle for the background. And what you're seeing on the right here is the density field. So what the model is doing is it tracks the materials within the different compositions and the pressure temperature space that it's in. And this is just showing that like a slab fully subducted through the upper mantle and into the lower mantle, having gone through all of these equilibrium phase transitions. So this is all accounted for in my general model setup. And this is kind of just the broad what I start with for all of my models. And what I'll get into next is building the location-specific model that stems from this sort of base setup. And I'm not going to show the full model domain again, since we're focused on the slab and the slab conditions. I'm really going to stay zoomed in on this central part here, but just keep in mind that I am using a much larger box and accounting for sort of the mantle dynamics around. So yeah, I'm going to jump into actually building the location-specific subduction models now that I've incorporated the elasticity and low temperature plasticity. So how we do this is by incorporating data we have from observations or observational models. So from observations, we can build specific geometries for slabs and thermal structures that are informed from observations. So for the geometry of the slab, we use the Slab 2.0 model for the slab geometries that tells us the depth to slab distance, shown with the color bar here, for all the subduction zones here, derived from seismic data. For the thermal structure of the slab, we can use observed plate ages and velocities to help set up half-space cooling models for the plates at the surface, and a newer mass-conserving temperature model for the slab to ensure a smooth temperature profile across the slab and into the mantle. And this is all done in Geodynamic World Builder, another open source code that CIG hosts that can be used to set up initial conditions and then fed into Aspect to run the numerical simulation. So I'm going to walk you through and then show you the results for one of these profiles. And here's just blown up a map of the Slab 2.0 data. And I'm going to focus on an example of the profile for the Kermadec-Tonga subduction zone. So in a little more detail, what you're seeing here is the light blue line is the trench where the plate is subducting. The royal blue lines are the simplified plate configuration. And again, that color scale is giving us an idea of plate geometry. So it's showing us that depth to the top of the slab at various locations. And I'm going to take a profile, trench perpendicular, extending from the trench there to build the slab geometry from the Slab 2.0 data, as well as bring in some regional tomography for the deeper parts of the slab to help inform that very deepest part of the slab. So that map over here on the left now, again, I've just labeled it A to A prime, but it goes across that Kermadec-Tonga trench. And what you're seeing on the right is the initial setup for that specific cross-section, where we have the geometry from the Slab 2.0 and also inferred from the regional tomography data here. And the temperature structure is set up for the slab and plates using the observed plates and ages that are brought into the temperature model here. And so this is what our sort of initial setup looks like for a location-specific model. So one of the challenges with this is I said earlier on that our models evolve with time according to density differences and run forward. But the point of building a location-specific model was so that we could compare with a specific location. So if we build that model and then run it forward and let it evolve, we're going to change that geometry we just set up. So the challenge was, how do we build up elastic stresses and approximate the strain rates while preserving that location-specific geometry we just set up? And so to do this, we developed something I'm going to refer to as the static method, the static modeling method, where I only advect the elastic stress tensors and I fix the composition and temperatures. They do not change. So those stay static and the elastic stress tensors are advected forward. A little more visual way of showing what this looks like is I'm actually going to show you a model run for that profile that we just walked through setting up. So on the left, what you're going to see is the magnitude of the stress field build up, and the white contours are just those same temperature contours I had in the initial setup to just kind of visually show you what that geometry is and how it's not going to change. And then on the right-hand side is the evolution of stress for this red point in the middle here. So as this model runs, you see the stress field evolve. We have white. I'll play it again since it's very quick. The white is the highest stress and the dark blue is the darker stress. And so we get this nice viscoelastic stress buildup and we get a well-resolved stress field in the end. So that's what the model looks like as it actually runs. And we can get out of this solutions for that profile of the magnitude of the strain rates shown here on the left and the magnitudes of the stress shown on the right. And so now we have our present day geometry with our approximated present day conditions. And I'm going to focus just on the strain rate for now, since if you remember, the initial goal was to be able to test this strain rate constraint hypothesis. So I'm going to shrink the part of the domain we're looking at just a little more, since we're focused on the seismogenic part of the slab where we see deep earthquakes, and look at the strain rates just from about 700 kilometers and up. And then I'm going to look at the strain rates just within the colder portion of the slab where we would expect deep earthquakes to occur. And so now I'm going to use that sort of same methodology that the Billen 2020 paper originally used of look at the strain rates within a specific temperature contour and plot them as a function of depth. So what you're seeing here is the strain rate within that temperature contour plotted as a function of depth. And then we can compare, and since these were specific location models, we can compare with the earthquakes for that specific profile as well. And so what you're seeing is the observed earthquakes for that same profile across Kermadec Tonga. The earthquakes are colored by depth. And then this is again one of the histograms where we're plotting the number of earthquakes as a function of depth. And so this is to demonstrate the sort of workflow and approach of how to use this. With this initial testing, you can see that there is a little bit of misalignment, but in general, our highest strain rates are below 500 kilometers depth, and that is where our highest number of earthquakes are. And so this is just sort of demonstrative that I've shown here of the utility of this location-specific method. But to really test the strain rate constraint hypothesis, I'm applying these methods to multiple 2D profiles along strike within a subduction zone, and then also look at multiple subduction zones, since like I said, or like I showed, different subduction zones exhibit different depth distribution behavior. So those were the two main goals for what sort of updates to the subduction modeling I wanted to do in order to test the strain rate constraint hypothesis. And along the way, had to develop this static modeling approach to be able to achieve this location-specific comparison. So we had our present-day geometry of the slab. We ran it forward using the static method to approximate the present-day stresses and strain rates. But something that you might be curious about is the slab has been subducting over millions of years to get to its present-day form. And in this method, we're not accounting for that history. We're just starting with the present-day shape and then running the model forward with this method to get the present-day stresses and strain rates. And so to prove to you and myself that this was a valid method, I am going to show you a proof of concept model that I developed to use a hypothetical subduction zone and demonstrate that this is a valid method and approach for approximating the present day conditions when we're leaving out this kind of long history of the subducting slab. And this long history is something that we will never really know for real subducting slabs. All we get is the present day snapshot. And I'll also just note that our understanding of subduction modeling and where the community is not at a place to be able to initiate a subduction model from a small little proto slab and have it develop an exact geometry that we would want for a specific location. So that's where the importance of developing this method came in. So the proof of concept method is going to be for a hypothetical subduction zone. And what it is broken down into 3 phases. The first phase is starting from just an initial little proto slab where the white temperature contours are going to be your kind of clue into the geometry here. And this is just run as a fully dynamic model for 10 million years where it just runs and evolves according to those density differences and the buoyancy forces, and we end up with our evolved present day state where we have our fully dynamic set of slab conditions, and we have, I'll just refer to the slab geometry P1 as our evolved slab geometry for phase 1. In phase 2, I'm going to preserve that geometry, so slab geometry P1, those white temperature contours are the same between the end of phase 1 and phase 2, but remove all those present day conditions of stress and strain rate that we just evolved. And then in phase 3, I'm going to use that static method of starting with an initial geometry, so we still have that slab geometry P1 that we've preserved across the phases, apply the static method, and end up with a solution that is the static evolution of slab conditions. And in this way, we'll be able to compare the stress and strain rate solutions of a fully dynamic slab with something that was statically evolved that has the actual same geometry. And this phase 2 to phase 3 is analogous to what I did for the Kermadec example, where I didn't have any of the stresses or strain rates. All I had was this geometry and temperature structure. what this looks like in practice is what you're going to see is the 3 phases run together. And in phase 1, the slab, like I said, begins from a protophase and starts subducting. You're looking at the stress field again. So white is high stresses and dark blue is lower stresses. And it's just going to evolve on its own. Remember, I'm not applying any velocities at the surface, and just end up at this sort of final phase or final point in the phase after 10 million years of our evolved geometry. Oops. There we go. So then in phase 2, as I said, we're going to take away those evolved stresses. In this case, you can visually see that that geometry is staying consistent, indicated by those temperature contours, but those evolved stresses are being removed. So now we're kind of back at that starting point of the location-specific models. And then in phase 3, we applied the static method to that same geometry that we had frozen, and we run a very short model and evolve our stress solution here. When we compare the stress orientations from the 10 million year run dynamic phase 1 solution on the left with the phase 3 static evolution on the right, we can see first order comparisons between sort of the spatial arrangement. We get a nice neutral plane with both regions are areas of high and low stress, though there's difference in magnitude. Spatially, there's good comparison. To look at this a little more quantitatively, what I've done here is just for 4 points that I selected from various depths within the slab, I plotted the stress as a function of time for each of these 4 points in a solid color line for phase 3. So as the model's running, what the stress evolution is for a particular point, and the dashed line is for that in the same color for that corresponding point, what the level of stress was at that point at the end of phase 1. So basically, is our stress curve reaching that dashed line that was this dynamically evolved stress? And we see that we are within about a factor of 2 of the stress reached in the dynamic model. And so we're getting a good approximation for the values of stress that we see in the slab. Additionally, we can compare the stress orientations. So these, what you're seeing here are the principal compression axes, and these are calculated from the stress tensor in the model, with the orange lines being the principal compression calculated using the static method, and the red lines being the principal orientations calculated using the dynamic method. And throughout the upper mantle and transition zone, we see pretty good agreement. A lot of the axes are aligned directly on top of each other. There is a little more disagreement down in the lower mantle, but this is sort of expected and also not as important for the deep earthquake problem that we're thinking about, since we don't observe deep earthquakes down here, and we won't be doing a lot of analyses down there since we don't have the observations to compare to. The strain rate comparisons also show good spatial comparison between, again, we see our neutral plane, we have our depths and tops and bottoms of the slab with higher strain rate and lower strain rate between the two. We also are able to reproduce some shear banding in the outer rise area of the slab between both the dynamic and the static solutions. So overall, we see good agreement that supports that this static method is a valid way to approximate the present day conditions. And just to kind of think about whether this is surprising or a weird result, again, our models are really driven by the density differences in the model. And when you have the same geometry and temperature set up, so this here is the end of phase 1, and this is the end of phase 3, with the white temperature contour showing that same preserved geometry, and the color field is showing the density solution. And so since they have the same temperature and composition structure, they have the same density setup between the two of them. And that's what's driving the model evolution. So plotted here are the velocity vectors for the model. So red, again, is phase 1, and orange is phase 3. And the flow fields are plotting right on top of each other as expected, because they have this same driving density structure and density differences within them. So now I hope this further proves that this is a valid approach and that we can take this sort of method, apply it to these future profiles within the Kermadec-Tonga region and to other subduction zones to test the strain rate constraint hypothesis using these new modeling methods. Another result of incorporating elasticity and building this for the specific locations is that we can look a little more at the stress orientations and a little more detailed context than with the not location-specific models. So shown here on the left of just in the narrower, colder part of the slab, plotted on top of the strain rate are those computed principal compression axes from the model. And then we can look at on the right, the p-axes from the CMT catalog for that same profile there. And we can start to make kind of more detailed comparisons and look at how does our model compare with the observations? And also, can we kind of go between the two to try and improve both of where in the slab are these earthquakes falling? Where are we seeing down dip compression or down dip extension? Is this on the top or bottom side of the slab? Because we have the elastic component, we have a lot of different localized regions where it's not just down dip compression for a whole section, but we're getting along the bending, down dip extension, and then down dip compression on the other side. So this is kind of a future direction that I'm working with to get this sort of more detailed analysis of the stress orientations that we're able to look at now, accounting for the elasticity and the location-specific models. So that is kind of answering those first two questions about what are the conditions, how do these compare with deep earthquakes, and I've shown you kind of the method and the roadmap forward. And then, as I said, I'll just kind of at the end here talk a little bit about this future work that I've started as well to think about how whether or not these hypothesized failure mechanisms that I mentioned are feasible in the deep slab. So I'll just talk about this last part at the end here of thermal shear instability. So I'm going to briefly walk through what thermal shear instability is, since I know everyone might not be familiar with it. But in kind of a cartoon schematic way, what we have is a block of rock shown in panel B here that has some sort of perturbation or weak zone indicated by this kind of kink in the blue bars here. And so we have a block of rock that has some sort of weak zone in the middle that when we start to shear and apply high stresses, we're going to end up localizing and deforming at very high strain rates in that weak zone within the block of rock. And as we continue to shear that block of rock, you're going to keep deforming at high strain rates in that localized region, and you're actually going to start to heat the material. And you're going to enter into this positive feedback loop where you're heating the material, and as you're heating it, you're also weakening it. And so then it's going to deform at even faster strain rates, cause more shear heating, make it weaker, and you're going to get into this positive feedback loop where eventually you're going to generate melt. And you can see the blue bars here have sort of released and snapped back. That would be your earthquake that occurred after the thermal runaway. So you're generating a lot of heat, eventually reaching a melting point, and the rock's strength is exceeded and your earthquake would occur. Our field evidence for that comes from exhumed pseudotachyte veins, so quenched glass that would have been this melt that occurred in the fault zone. And the evidence for it for deep earthquakes is from finding these pseudotachytes within ductile fabrics. So this one shown here was a pseudotachyte found surrounded by myelinites. So evidence that we're in a more ductily deforming region, not brittly, but then we're getting this melt to occur there. And so, excuse me, with numerical modeling, we can investigate this question of if we have a given set of conditions for one of these blocks of rocks here, can thermal shear instability initiate? So I'm not going to go into the big details of this model, but this is a model developed to look at shallow or deep earthquakes by Marcel Thielman, But what he set up is basically a block of olivine here that has a weak zone already set up in the middle where our deformation is going to localize, prescribe initial conditions, so temperature, grain size, stress, strain rates, start deforming that box, and see whether or not the thermal runaway process will initiate and whether you get thermal shear instability. So it's, again, I think for the sake of time, I'm not going to talk about the details of it, but it's basically to answer whether this process can initiate or not. And I'll just note that it doesn't simulate any of the processes after that melting would occur. So it doesn't tell us anything about size of earthquake, but really, is this process possible at these conditions or not? And so the way to sort of link numerical models and now use these subduction models as a lens to guide our investigation of this mechanism is we have our updated subduction modeling methods, and we can select conditions from those models. So where we think deep earthquakes are occurring, regions of high strain rate, high stress, low temperature, and we can use those as that set of initial conditions in this separate thermal shear instability model and test whether or not for that set of conditions, do we see this process initiate? And we would run this for a suite of conditions selected from throughout the slab to sort of test this variability of where do we see it to be feasible or not feasible. And the goal here is not to say like thermal shear instability is like the mechanism and that the other mechanisms are not feasible, but it's more so just about whether or not this is feasible at the conditions that we're seeing or not, and where we actually are seeing earthquakes occur. If they're in regions where we don't see TSI being feasible, then maybe one of these other mechanisms is the trigger for those earthquakes. And then, yeah, also the last thing about this part is that this workflow of taking the subduction modeling conditions here and feeding them into be the initial conditions of the TSI model is a workflow that could be applied to testing the other failure mechanisms as well. So using numerical models for the other mechanisms by kind of feeding them the initial conditions that were the outputs of the subduction model. So the overall takeaways for today's deep earthquake focused talk is the updated subduction modeling methods I presented. We're building these location-specific models that had a viscoelastic plastic rheology, and these allowed us to approximate the present-day slab conditions and have a more direct comparison with the actual deep earthquake observations. I also showed you a proof of concept model supporting the validity of this newer modeling approach that we developed, and just kind of overall that these newer methods are allowing us to test the strain rate constraint hypothesis that was proposed a few years ago, and also inform the investigation of thermal shear instability viability in the deeper slab than it has been investigated previously. So with that, I will take any questions, and thanks for listening.
All right. Thank you so much, Vicky, for this very excellent and insightful presentation on deep earthquakes on the mechanisms from the perspective of numerical modeling, and also some comparison between your modeling results and also the seismic observations. All right, so now we would like to open for questions the audience may have. Please type your questions in the chat. We have one question from Colin Wang. Thank you for the nice talk. How is the model predict stress direction compared with focal mechanisms?
So is the question like, what is the method for doing this, or like how does the comparison look? I guess I can answer both. So how it's done is by taking the p-axes from the CMT catalog and projecting those onto the 2D plane that our profile is through. Oh, it's about the results. Okay. Yeah, so the comparison, can go back to that. So the general comparison, let me see if I can scroll over, is that we are reproducing things sort of generally known from observations, such as sort of like down dip compression throughout the slab, changes in the stress orientation as the slab is bending and unbending. So we're reproducing some of those general features. When we're comparing with the location-specific ones, this is going to take a little more investigation to kind of think about translating these earthquake observations into the model space, and also keeping in context that the geometry of the slab is built from the Slab 2.0 data, which is also a sort of model built from the observations. And so I'm not at this point doing a point-by-point comparison between the modeling p-axis results with the earthquake observations, more so looking at the broad patterns. And then I plan to do a more detailed way of looking at how to kind of account for maybe some of the limitations of the Slab 2.0 catalog being more of this model and where the actual earthquakes are occurring in real space. So overall, we're reproducing kind of general observations that we see, but it's hard at this point to do the point-by-point comparison. That's something I'm working on next.
All right. We also have a question from Gabriela Hobson. So hi, Becky, thanks for an awesome talk. I need to read those questions so the other audience can know what the question is. So really interested in this work. I have a quick question about your static method. In the case that represent specific subduction zones, how does your temperature fields develop if the velocity are not prescribed and the slab geometry is held fixed? I understand you initiate with a half space cooling model, but how does it involve? This is about the details about your method.
Yeah, it's a good question. So the temperature does not evolve during the static method. It's only run for 150,000 years. And so the temperature that we set at the beginning is constant during the static method. So I'm not prescribing in terms of like setting the half space and the mass conserving temperature models. I am using the velocities there for building the temperature model, but not prescribing them as like a velocity boundary condition. So they're being accounted for in terms of the temperature structure and what like the slab temperature at depth would be based on its subduction history, but it does not evolve during the static method, since they're only run for a short time.
Okay, Becky, actually, I have a question.
Yeah.
So, you see a nice correlation between the high strain rate, depth range, and the density of the deeper earthquake depth distribution. So I'm curious why those regions, those depths has high strain rates. Is that because the geometry, or is something else?
Yeah, it's a good question. So the higher strain rates are usually associated with the bending and unbending of the slab. And so as the slab is like going through the transition zone, and especially like all the phase transitions where you're getting a lot of variations in the density structure, as the slab is bending and unbending is where you get these higher strain rates. And this is something that's been seen in a lot of modeling papers in the past too. So that's not something newer. It's more so the tie to the deep earthquakes, but it's something seen in models with just overall slab deformation, is this bending and unbending where we're seeing the high strain rates. So in this case, the example that I showed, we have it entering the lower mantle, and it kind of is getting into this flatter slab geometry. So we have this bigger bend there that would be associated with the higher strain rate.
Thank you. Oh, we have another 2 questions. One from Sun Tian Hao Zhe. So excellent talks. Thanks for incorporating elasticity. What kind of shear modulus are you using, and how important is this effect? Given the large slab deformation over time, it might has reached yielding almost everyone, and the pervasive failure makes the slab very weak elastically.
So for the elasticity, I am using a constant value of about 1 × 10⁻¹⁰ pascals, which is value associated with deeper depths. But since I was applying 1 shear modulus to the whole model, I went with that one. I don't know. I tested out different shear moduli earlier in the model development with sort of the final model setup. I haven't tested it to see. It will affect what sort of values you're getting out, because it'll affect how strong the elastic component is compared to the viscoplastic parts. But I don't have an answer in terms of like how important it is and like what sort of magnitude changes you would see. I don't think it would change the overall results of the where we're seeing the higher strain rates versus the lower strain rates with the bending and unbending, because this is something observed also in like purely viscous models. But I think it would be important for the magnitude of the values we're getting out. And I do have, in terms of the yielding, I do have the low temperature plasticity and Drucker-Prager yielding criterion. So I do have like a more specific or more kind of explicit yielding incorporated there. If that answers that question.
All right, we also have a question from Pablo. Thank you for the talk. Really interesting. I noticed the shallower parts within 300 kilometers seems to have a higher discrepancy. Do you think the static approach might actually have particular limitations in that range that are not important when you go deep? Do you have a preliminary interpretation for that high discrepancy?
I think they're talking about this discrepancy.
Yeah, within 300 kilometers.
Okay. Yeah. So I have some ideas. What I'm plotting here is sort of the minimum strain rate within that narrow band for just one of the temperature contours. But also temperature and stress are important, as I mentioned, for where the deep earthquakes are occurring. And so I think for this first order slice here, yeah, I can't like explicitly think of like one thing that would cause this discrepancy. But yeah, I don't think that it is a particular limitation of the static approach. Yeah, I don't think so, because of the types of comparisons that I did in the proof of concept model throughout this lab of comparing the stress orientations and the stress magnitudes. It's sort of a more in the not location specific model. So I don't think it has to do with the static method. I think it has to do more so with limitations regarding that these are 2D models and not 3D models, and that we are using the Slab 2.0 data, which might be smoothing some of the more detailed variations that we see in the slab. And so I think it'll be really important to do these multiple 2D profiles across the slab to try to get at the 3D picture, and might see something more clear pop out because the earthquakes are occurring in 3D space, but I am only modeling 2D space here. But yeah, I don't think it has to do with the static method itself. I think it has to do with the observational modeling limitations.
All right, we have another question from Colin Wang. So model differential stress seems to be up to a few 100 MPa. Does this lead to plastic yielding at such high pressure?
We do see yielding, some yielding in the deep slab. We see some of these, like the shear band showing up in the strain rate solution.
Okay, I think those are all the questions in the chat. I also have one question about, actually you already mentioned that in your answer to one previous question. So you're doing 2D modeling. Do you have any plan for 3D? And what's the real motivation and also the limitation to do the 3D modeling?
Yeah, so it's a good question. I don't currently have a plan to do this in 3D. The 3D models are a lot more computationally expensive. The 2D models can run with a lot less computing power. And so for now, my plan is to try to get at the 3D picture. It's still limited, but try to get at it by doing multiple 2D profiles close together along the trench, along like a swath of the trench. But yeah, I mean, the 3D models would get at the 3D picture of the space that the earthquakes are actually occurring in. But yeah, that's not something I have done with this. But I mean, I think it would definitely be a very good step. It's just not one that I currently am working on. And it also does greatly increase the computational cost of running the models. But yeah.
Yeah, that makes sense. Thank you. Thank you for your answer. All right, so if I did not see more questions here. Okay. If there's no more question, let's thanks Dr. Faiz again for her excellent talk. Very interesting work. And don't forget to fill in the survey to provide us some feedback about this webinar. And thanks everyone again for your presence today. And we looking forward to see you next week. All right. Thanks, speaking.
Thanks. Thank you.
Bye. Bye, everyone. Take care.